We're going to be looking at a few different topics in Chapter 4, but the first one that we're going to talk about is how to transform your data to achieve linearity. So back in Chapter 3, we spent that chapter talking about how to create a line of best fit if you have a set of data that is linear, and we talked about how to determine whether a linear model is appropriate for a given data set using the scatter plot, then looking at the correlation coefficient, and then also creating a residual plot and taking a look at the shape of that residual plot to see if a linear model is appropriate. But we also said that for our purposes in this class, we only want to look at data that is linear. But what happens if you get a data set that is decidedly not linear? And here's a scatter plot that I just happened to make up, and you can tell that it's not linear, but you can also see that there is a bit of a pattern to it. Here's just a general shape of what a function might look like if you're trying to use a function to describe this data. And you can tell that it's got a curve to it instead of being a linear model. So what happens if we are given a data set that is decidedly not linear? Do we just ignore it? Can we do nothing to analyze it? And the answer to that is no. What we're going to do is we're going to transform it to try to take it from a non-linear model and turn it into a linear model so that we can then treat it as if it was a regular linear data set, and we can still run our least squares regression. We can still come up with a model for our data and make some predictions with it. So there are a few basic types of transformations. We've already talked about one. We talked about it back in the first chapter, and those were linear transformations. And that was basically just changing the units of a set of data. We were either taking our data and multiplying everything by a constant, so we were scaling it up or down, or we were shifting our data to the left or to the right by adding or subtracting a value to it. And a linear transformation isn't going to do anything for us, meaning multiplying our data by a constant or adding a constant to our data. That's not going to help us out if we're faced with a situation where our original data set is not linear. So the linear transformations that we talked about in Chapter 1 aren't what we're going to be looking at here in Chapter 4. What we're going to be interested in is performing either a power transformation or a logarithmic transformation. And in subsequent lessons, we'll talk more about how you know which type of transformation that you're going to want to perform. But let's say that you are presented with that data set or that scatter plot that I showed you earlier, and we already said that we can tell that there is some sort of pattern to this scatter plot, but it's definitely not linear. It actually, if you remember back to Algebra 2, or for those of you who are in pre-calculus this year, you might be able to tell that this is more of an exponential type of data set. So what we're going to be doing in this section is we're going to be taking our original data that we've got in this first scatter plot, and then we're going to be applying some sort of transformation, whether it's a power transformation or a logarithmic transformation. And when we do that and we create a scatter plot with our newly transformed data, our goal is to then get a scatter plot like you get in this one on the right, this one here, where our data now definitely follows a more linear pattern. And you can see that I drew in purple my estimate of where the line of best fit would be. Now it looks like we have truly achieved linearity with our data in this second transformed scatter plot. But then our next step is going to be create the residual plot, like I did down here at the bottom, to confirm that we have indeed created a linear or an accurate linear model for our data. And keep in mind, like we talked about in the last chapter, when you create a residual plot, you know that that a linear model is an appropriate model for your data set if there isn't any sort of pattern in the residual plot when you plot your points. And as you can see in the residual plot that I've created, the plots are scattered pretty equally above and below the line. So it does look like a linear model would be appropriate. So this is the basic gist of transforming data to achieve linearity. Like I said a moment ago, in subsequent lessons we'll be talking more about how you know when to use a power transformation versus when to use a logarithmic transformation.